Let's move on to another definition. And here we can see that the derivative of a function f at a number a, denoted by f prime of a, is limit f of a plus h minus f of a divided by h as h approaches 0 if this limit exists. And again, f prime of a equals to limit of f of x minus f of a divided by x minus a as x approaches a. So this is just to sum up that yes, we have two different ways to write the derivative, and both of these formulas are equivalent as I mentioned earlier. So now we will use any of these formulas to compute the derivative at x equals to a and at x equals to 2 of the function f of x equals to x squared minus 8x plus 9. So I will choose the formula with the h. So let's compute the derivative. Limit of f of a plus h minus f of a divided by h as h approaches 0. So what is f of a plus h? So f of a plus h is a plus h squared. So in order to find a plus f of a plus h, anywhere I see x, I plug in a plus h minus 8 times a plus h plus 9. So this is f of a plus h. Now let's find f of a minus a squared minus 8a plus 9. All of this divided by h. Now, let us expand the numerator. We get a squared plus 2ah plus h squared minus 8a minus 8h. If you lost the track, these first three terms are from the a plus h squared. 8a, negative 8a minus 8h is from this second parentheses. And then I have a plus 9. And then from this third or last term, I make every term negative inside. So minus 8 squared minus times minus is plus 8a minus 9. All of this divided by h. This leaves me with, let us simplify the numerator. A squared and a squared cancel each other. Negative 8a plus 8a cancel each other. Plus 9 minus 9 cancel each other. So this leaves me with 2ah plus h squared minus 8h divided by h. And as you might notice, there are h's everywhere. So let's factor the h in the numerator. This leaves me with 2a plus h minus 8 divided by h. And now let us cancel the h from the numerator and the denominator, which leaves us with limit of 2a plus h minus 8. And now let's plug in h equals to 0, and we get 2a plus 0 minus 8. So this is equal to 2a minus 8. And this is the derivative at the point x equals to a. Now let's find the derivative at the point x equals to 2. Simply plug in 2 instead of a. So 2 times 2 minus 8 gives us 4 minus 8, which is negative 4. And this is the derivative at the point x equals to 2. And let us continue. So the instantaneous rate of change, limit of delta y divided by delta x as delta x approaches 0, is equal to the limit of f of x2 minus f of x1 divided by x2 minus x1 as x2 approaches x1. And this is the definition we established at the start of this video. This is just to tell us that the derivative is the instantaneous rate of change of y equals to f of x with respect to x when x equals to a. So now we have maybe several definitions of the derivative. They all in fact are they all are the derivative. But now we can see that the derivative, as we saw earlier, the derivative is the slope of the tangent at a point, and the derivative is the instantaneous velocity at a certain time. And now we are seeing that the derivative is, in fact, the instantaneous rate of change of y equals to f of x at a point. So you can see there are several definitions of the derivative, and we will apply this one. So now, with this example, a manufacturer produces bolts of a fabric with a fixed width. The cost of producing X yards of this fabric is C equals to f of x dollars. What is the meaning of the derivative f prime of x? So we will ignore the last part of the question that asks for the units. For now, we will just define or just explain what is the meaning of the derivative f prime of x. So as we saw in this definition, the derivative is, in fact, the instantaneous rate of change of, let's look at the definition, it's the instantaneous rate of change of y equals to f of x. In our example, c equals to f of x with respect to x. So this is basically how much the y value is changing with respect to the x value. So how much, in our case, c is changing with respect to the x value. So what is c? C is the cost. So in other words, f prime of x can be explained as the rate of change of the production cost, because C is the production cost, with respect to x. So with respect, what is x? With respect to the number of yards produced. And this is what the derivative of f prime of x, this is how it would be explained in this example. So what I wrote at the top here is a small summary that the derivative can describe the instantaneous velocity at a certain time. It can describe the slope of the tangent line at a certain point, and it can also describe the instantaneous rate of change at a certain point. So now let's look at the notations. The first notation to describe the derivative is f prime of x. The second one, y prime. So the third one and the fourth one are quite similar, and they are in fact called Leibniz notation. You don't need to know what they're called, but just one thing to know about them is that what's the variable up here is the dependent variable, and the variable down is the independent variable. So when we are taking the derivative, we are taking it with respect to the variable that's written down here. So in case you're not used to it now, you will get used to the notations with practice. So don't worry about that much. Now let's use what we have learned so far about derivatives being the slope of the tangent line. Let's use what we know so far, and let's try to find the equation of the normal. So the normal is the line that is perpendicular to the tangent. So let's look at this graph. If the tangent at point A is this line that I'm highlighting right now, then the normal is the line that I will highlight in green. It also passes through the point A. And if the slope of the tangent is m, to find the slope of the normal, we have to take, because the normal is perpendicular to the tangent, we have to take the negative reciprocal. So first we put a negative sign and then we take the reciprocal. Reciprocal means flipping the numerator and the denominator. So the slope of the normal would be -1 over m, which I wrote right here. Now let's say we have the function f of x equals to x squared minus 8x plus 9. Let us find the equation of the normal line at x equals to 2. First of all, find the slope of the tangent. And in fact, since we said the slope of the tangent is the derivative, we already did this exercise. We found the derivative before. Let's go up to where, let's find this question. So in fact, here it is. So we found the slope at x equals to 2, the slope of the tangent line, to be -4. So let's use what we found. So the slope of the tangent is -4. Step 2 is find the slope of the normal. What is the slope of the normal? It's the negative reciprocal. So first negative of -4 is +4, and then the reciprocal of 4 is 1 over 4. So this is the slope of the normal. And as you know, the equation for a line is y equals to mx plus b. We have found the slope to be 1 over 4. And regarding finding a point, we are finding the equation of the normal at x equals to 2. So our x value is 2. What is the y value when x is 2? So when x is 2, f of 2 is 2 squared minus 8 times 2 plus 9, which is 4 minus 16 plus 9, which gives us -3. So the y value is -3. So now this leaves us with -3 is equal to 2 divided by 4 is half plus b. And if we solve for b, we get b to be -7 over 2. So let's write our equation. Y equals to the slope. So 1 over 4x plus b, so -7 over 2. And this is our answer. Now let's continue with the explanations a bit. So the derivative of a function, up until what we were doing before, we were looking at the derivative at only one specific point. Now, what if we want to find the derivative of a function? So, first of all, at a point we had to find the derivative or the slope of the tangent at a point. What we did was the limit of f of a plus h minus f of a divided by h as h approaches 0. And as you might notice, a is a constant. However, in a function, we have x, which varies. So simply to find the derivative of a function, all we have to do is generalize this function and use x instead of a. So our formula becomes limit f of x plus h minus f of x divided by h as h approaches 0. And in fact, this part, we call this the difference quotient. So let's look at a few graphs and a few examples. So let's look at these two graphs. The first graph up here is the graph of f of x, and the second graph is the graph of the derivative of f of x. So as you might notice, let's look at point A here. The tangent at point A, its slope is negative. This means in the graph down here where we have the derivative at point A, it's negative. You see this is 0, this here is 0, it's below 0, it's negative. Now let's look at point B where the slope of the tangent line, the tangent is horizontal, so the slope is 0. So in the graph of the derivative, the point here is 0. Now let's look at point C. The tangent has a slope of 1. It's increasing. So in the graph of f prime of x, at point C, we have a value that's positive. At point D, since the tangent is horizontal, so the slope is 0, at point D we have a value that's 0 in the graph of the derivative. Now, at point P, the slope is around -2/3. So we have a point that's negative. It's -2/3 down here in the graph of the derivative. So you can analyze graphs of derivatives in this way. However, sometimes you will not be given these values of m equals to -1, m equals to 0, but it is enough to look, let's say at point A, to look at the tangent line. You will realize that its slope is negative, therefore you will have a negative value in the graph of f prime of x. And now let us do an exercise. Find f prime if f of x equals to 1 minus x divided by 2 plus x. This comes from the book, page 156. So again, let us use the definition in order to find f prime, or the derivative. So let's start by writing f of x plus h minus f of x divided by h, the limit of this as h approaches 0. And now let us plug in what is f of x plus h. Basically, it's the function, and everywhere you see an x, instead of the x, you write x plus h minus f of x, all of this divided by h. So now, let's simplify this. Let's combine the fractions. First of all, in the numerator of the first fraction here, we have 1 minus x minus h. We distribute the negative, divided by 2 plus x plus h. And the second fraction stays the same. Now, let us find a common denominator. So maybe a common denominator would be the denominators of both fractions multiplied. So we would have 2 plus x plus h times 2 plus x. And since I multiplied the denominator of the first fraction by 2 plus x, I have to multiply the numerator by 2 plus x as well. So I get 1 minus x minus h times 2 plus x minus, again, the same denominator, 2 plus x plus h times 2 plus x. And since I multiplied the denominator of the second fraction by 2 plus x plus h, I also have to multiply the numerator by 2 plus x plus h. And now, let's put these fractions, let's write them as one fraction with a common denominator of 2 plus x plus h times 2 plus x. So in the numerator, we would have, let's expand the numerator. So 1 times 2 plus 1 times x gives 2 plus x. Now, negative x times 2 and negative x times x. This would give negative 2x minus x squared. Now negative h times 2 and negative h times x would give negative 2h minus hx. Let's look at the second fraction. Don't forget the minus sign outside. So 1 times 2, 1 times x, and 1 times h. This would give us 2 plus x plus h. And now negative x times 2, negative x times x, negative x times h would give us negative 2x minus x squared minus hx. Now let's rewrite this fraction in a better way. In fact, we can write this denominator, we can write it down below next to the h. So let's do that. Let's write in the denominator h times 2 plus x plus h times 2 plus x. And let's leave the numerator the same. We can distribute the negative inside, so minus 2 minus x minus h plus 2x plus x squared plus hx. Now, if we were to plug in the h, we would get 0 over 0. So let's continue simplifying. We see that the 2 and the minus 2, they cancel out. There is an x and the minus x, they cancel out. We have a 2x and the minus 2x, they also cancel out. We have an x squared and the minus x squared, they also cancel out. And we also have hx and minus hx, they cancel out. So let's see what we are left with. The limit of negative 2h minus h divided by h times 2 plus x plus h times 2 plus x as h approaches 0. We can even simplify the numerator. Negative 2h minus h is negative 3h. And now since we have an h in the numerator and the denominator, we can cancel the h. And this leaves us with the limit of negative 3 divided by 2 plus x plus h times 2 plus x as h approaches 0. Now let us plug in h equals to 0 to see what we get. We get negative 3 divided by 2 plus x plus 0 times 2 plus x, which is equal to negative 3 divided by 2 plus x all squared. And this is our answer. And now let's move on to another example. If f of x equals to square root of x, find f prime of x and the domain of f prime of x. This comes from the book, page 155. So let's start by finding f prime of x, derivative. So let's start with the definition of the derivative of a function. Its limit of f of x plus h minus f of x divided by h as h approaches 0. Now, what is f of x plus h? It's the square root of x plus h. F of x is square root of x divided by h as h approaches 0. And now, if we were to plug in h equals to 0, we would get 0 over 0. And this is a sign for us that we should simplify this in some way, maybe rationalize here because we have a lot of square roots. A reminder that this is square root of a minus square root of b. If I multiply it by square root of a plus square root of b, I would get a minus b. So let's do that. So I will multiply it by square root of x plus h plus square root of x. Again, I should multiply the numerator and the denominator. And this would give us, as I said in the numerator, it would give a minus b. And in the denominator, h times the square root of x plus h plus the square root of x. And now in the numerator, I have x minus x. I can remove them. This will leave me with limit of h divided by h times x square root of x plus h plus the square root of x. I have h in the numerator and denominator. I can cancel them out. This leaves us with limit of 1 divided by square root of x plus h plus square root of x as h approaches 0. And now let us plug in h equals to 0. What do we get? We get 1 divided by square root of x plus square root of x, which is 1 divided by 2 square root of x. This is f prime of x. 1 divided by 2 square root of x. So, let us find the domain of f prime of x. So first of all, let's look at what we have. We have a square root. One thing to note about square roots is that what's inside the square root has to be greater than or equal to 0. Also, 2 square root of x is in the denominator, so it has to be different than 0. We know that 2 is different than 0, so square root of x also has to be different than 0. We square both sides. We get that x has to be different than 0. So as a conclusion, yes, we know that x is greater than or x should be greater than or equal to 0, and x should be different than 0. So we write the domain is x greater than 0. This is where this function exists. Now what's really weird about this is that this is f prime of x. F prime of x, the domain of it is when x is greater than 0. However, f of x equals to square root of x, its domain is x is greater than equal to 0. So we can see that f of x and f prime of x do not necessarily have to have the same domain. They can have different domains. So let's look at another example. F of x equals to absolute value of x. Let's try to find the derivative at x equals to 0. So now we are back to finding the derivative at a point. So let's use one of the definitions we learned, which is limit of f of x minus f of a, in our case a equals to 0, divided by x minus a as x approaches 0. So limit of f of x minus f of 0 divided by x minus 0 as x approaches 0. So this is the limit. What is f of x? It is absolute value of x. What is f of 0? So absolute value of 0 is 0. We don't have to write this. And in the denominator, x minus 0 is x. And now, as we learned in previous videos, whenever we have an absolute value, we can split this into two limits, one coming from the left and one coming from the right. So from the left, we get, instead of absolute value of x, we get a negative x in the numerator, and then the denominator remains x. So let's compute this limit. This becomes, so I will write it in more details, limit as x approaches 0 from the left, of negative x divided by x. I can cancel the x from the numerator and the denominator to leave me with a negative 1. So this becomes negative 1 because the limit of the constant is the constant itself. As for the limit coming from the right, I can rewrite this absolute value as x. So I get the limit as x approaches 0 from the right of x divided by x. So what is x divided by x? It's 1. So this is the limit of 1, and the limit of a constant is the constant itself. So we can notice that the left-hand limit and the right-hand limit are not equal. Therefore, the overall limit does not exist. In other words, we were not able to find the derivative. So the derivative does not exist. Let's look at a few cases when the derivative does not exist. So, the derivative does not exist when we have a sharp corner like the absolute value. The derivative does not exist when we have a curvy corner. This we also call a cusp. The derivative also does not exist when we have a vertical tangent, as we can see here. And it also does not exist when we have a discontinuity. So these are the 4 cases when the derivative will not exist. Now let's look at a theorem. If f is differentiable at a, then f is continuous at a. This is a theorem, and the converse, the opposite of this theorem, is not true. The reason why, look, this is an example with absolute value. It is continuous at 0, but it is not differentiable. So the other way around of this theorem is not true. I will write this down here. The converse is not true. Now let's look at the proof of this theorem. So this is taken from the book. To prove that f is continuous at a, we have to show that the limit of f of x as x approaches a is equal to f of a. This is how we show continuity. We learned this in a previous video. So we will do this by showing that the difference f of x minus f of a approaches 0. The given information is that f is differentiable at a. So this is what is given in the theorem. So because we are starting with if f is differentiable at a, so assuming that f is differentiable at a, then f is continuous at a. So we are assuming that it is differentiable. So this limit is the derivative. The derivative at point A is equal to limit f of x minus f of a divided by x minus a as x approaches a. Since we are assuming that it is differentiable at a, then this limit in fact does exist. So we will start with our proof. So we will start by using f of x minus f of a. What we will do with this is that we will multiply it and divide it by the same factor. This does not change anything because this factor is not 0. It's x minus a, and x is different than a. So it's as if you're saying that we have the number 2, I'm multiplying it by 3 and dividing it by 3. So I still get a 2. So we still get, it's still the same thing. We're still f with f of x minus f of a. However, the reason why we did this is now we can use limit laws. So let's take the limit of f of x minus f of a. So we're taking the limit of this entire thing. So when we take the limit of f of x minus f of a times x minus a divided by x minus a, we can now separate this into 2 limits. So we have the limit of f of x minus f of a divided by x minus a times the limit of x minus a as x approaches a. Now let's look at this first limit right here. What is this? This is f prime of a. We learned this at the start of this video. And now what is the limit of x minus a as x approaches a? We plug in a into x minus a, we get a minus a, which is 0. So now f prime of a times 0 is 0. Now let's continue. So in fact, what we wanted to do from the start is to prove that the limit of f of x as x approaches a is f of a. So this is not what we found. We found the limit of f of x minus f of a as x approaches a to be 0. So now we need to maybe modify and play around with this in order to reach limit of f of x as x approaches a. So what will we do with it? In fact, the limit of f of x as x approaches a, we have the f of x here. What did we do to the f of x? We added f of a and we subtracted f of a. Again, this does not change anything. This is as if I'm saying 2 plus 3 minus 3. It will still give me 2. So I added and subtracted the same number. So I added f of a and subtracted f of a. And why did I do this? In order to split the limit. Now I have the limit of f of a as x approaches a. plus the limit of f of x minus f of a as x approaches a. And regarding the first limit, this would give f of a. And regarding the second limit, if I plug in a in the place of x, this would give me f of a minus f of a, which is 0. So the second limit gives 0. And f of a plus 0 is f of a, and we have proved what we wanted to prove. So we have proved that the limit of f of x as x approaches a is equal to f of a, and this is how we prove continuity. Therefore, f is continuous at a. Now I just wanted to point out that at this point it is time to check the next video about derivatives and their proofs.